Imagine if the same graphics card you use to play games was secretly one of the most powerful scientific tools on the planet. You click Run, and a task that used to take all night finishes before your coffee even cools down. Weather simulations, medical scans, financial models, AI training, things that once needed huge, expensive supercomputers suddenly become possible on a single machine under someone's desk. That shift didn't happen by accident. It happened because people figured out how to turn a chip designed for drawing pictures into a general-purpose engine for doing lots of things in parallel. That's what GPU parallel computing and the CUDA programming model are all about, and today we're going to unpack it in a way that anyone can follow. Before we dive in, if you enjoy understanding the hidden technology that quietly runs our world, hit that like button, subscribe to the channel, and tap the notification bell. It really helps more people find these videos, and it tells me to keep making deep dive explainers like this one. Let's go back to the core problem this all solves. For years, computers got faster mostly by cranking up the speed of a single brain, the CPU. Higher clock speeds meant more work done per second. But pushing that speed too far turned chips into tiny heaters, and power and heat became serious problems. At the same time, the world wanted more. High-resolution video, 3D games, realistic physics, huge datasets, and more complex scientific simulations. Just making one core faster wasn't working anymore. Graphics cards, GPUs, took a different path. Instead of trying to have one incredibly fast thinker, a GPU is like hiring an entire army of decent thinkers. Each one isn't as sophisticated as a top-end CPU core, but when you have hundreds or thousands of them working together, they can blast through enormous piles of similar tasks. Drawing every pixel on your screen is a perfect example. You don't need one genius to decide the color of every single pixel. You need a crowd that can all do their little piece at the same time. Inside a modern GPU, that army is organized into groups. You can think of the chip as a city filled with many identical neighborhoods. Each neighborhood has a group of workers, some local storage, and a supervisor who decides which group works on which part of the job. The neighborhoods in a GPU are called multiprocessors in technical terms, but you can imagine them as mini-computers inside the bigger computer. Now here's the key insight that changed everything. Those workers don't have to draw pictures. If you give them the right kind of instructions, they can simulate the weather, analyze medical images, search a database, or train a neural network. The trick is to give normal programmers a simple, clear way to describe those tasks so that the GPU can handle the messy scheduling and coordination automatically. That's where CUDA comes in. CUDA introduced a simple mental model for using this army of workers without needing to think about all the low-level details. The idea is to break your big problem into many tiny, similar tasks and then let the GPU run a huge number of them in parallel. Imagine you're painting the giant mural. Doing it alone would take forever. CUDA's way of thinking says, first, divide the mural into a grid of small squares. Next, hire a bunch of teams. Each team is in charge of a patch of squares. Within each team, every person gets a few squares of that patch. In the real GPU world, that big mural is your overall computation, like processing every pixel in an image or every entry in a big table. The teams are groups of threads, small units of work, that cooperate closely, and the individuals inside each team are the separate threads themselves. Each team goes to work on its assigned patch, and all the teams operate at the same time. They don't need to talk to each other much. They just need to know what part of the mural, or what portion of the data, they're responsible for. This independence is incredibly important. It means the GPU can hand out teams to its many neighborhoods however it likes. If the chip you're using has only a few neighborhoods, it will run fewer teams at once. If it has many neighborhoods, it can run a lot more in parallel. Either way, the way you describe the work stays the same. That's one of the big superpowers of this model. The same program can run on different GPUs without you changing your logic. The GPU takes care of how many teams to run at once and when. You just define the big grid of work and how it's broken into teams. Now let's talk about the workers themselves. Each worker is like a very small, efficient employee following a list of steps. Workers are organized in groups that move in lockstep, like a row of assembly workers all performing the same step at the same time, just on different parts. If an instruction says, add these two numbers, every worker in that group tries to add their own two numbers at the same moment. What happens if they need to go in different directions? For example, half of them need to follow one if branch, and the other half need to follow another. The system handles that by temporarily splitting the group. It walks through one path while some workers wait, then walks through the other path, and finally brings everyone back together. You don't have to manually orchestrate this. The GPU does it for you. The important point is that the hardware is built to do the same simple operation across many pieces of data at once, very efficiently. To make this actually usable in real programs, we also need to think about how data is stored and shared. The memory system in this world is another layered story. Picture it like this. Each worker has a little notepad. That's its private space, where it keeps its own numbers and temporary results. Each team has a whiteboard in the middle of the room. This is shared space that everyone on the team can read and write to very quickly. They can use it to share partial results, coordinate, and avoid going back and forth to slower storage. The whole building has a big archive room. That's the main memory of the GPU. It holds all of the input data and final results, but it's slower to walk down the hall and grab something from there. The magic comes from using that whiteboard, the shared memory within each team, wisely. Instead of every worker constantly walking to the archive room to fetch the same data, one worker can grab it once, write it on the whiteboard, and now everyone can use it quickly. When you scale that up to hundreds of teams and thousands of workers, those savings add up to big performance gains. Of course, there's also the question of how the main computer and the graphics card talk to each other. In this setup, you can think of the traditional CPU as the project manager and the GPU as the giant workshop. The project manager plans the job. It decides what needs to be done, arranges the data in memory, and then sends the right files down to the workshop. The GPU workshop then calls in its teams, splits the work across all the neighborhoods and workers, does the heavy lifting, and hands the finished results back up to the manager. A typical workflow goes something like this. The CPU prepares the data and sends a copy of it to the GPU's memory. Then it tells the GPU, run this kind of task on this many workers arranged in this kind of grid. The GPU takes over, divides the work among its neighborhoods, and runs countless tiny tasks at once. When it's finished, the CPU pulls the results back and continues with whatever needs to happen next, saving the data, showing it on screen, or kicking off another round of processing. What makes CUDA so important is that it wraps all of this complexity in a way that feels natural to someone who already knows how to write regular programs. Instead of forcing you to learn a completely alien way of thinking, it keeps familiar ideas and just extends them with the notion of thousands of lightweight workers operating in parallel. You don't have to tell the GPU exactly when to switch from one worker to another or how to recover from delays when a worker is waiting on data. The hardware scheduler in each neighborhood does that on its own, constantly shuffling which groups are active so that there's always something ready to run. Once this architecture and model were in place, it opened the floodgates. Suddenly, people in many different fields could take advantage of this massive parallelism. Scientists doing climate modeling or earthquake simulations could speed up their work dramatically. Instead of waiting days for a forecast or simulation to finish on a traditional system, they could use GPUs to crunch through huge grids of numbers far faster. In oil and gas exploration, companies could process seismic data, basically echoes from the Earth's underground layers, using GPUs to build detailed 3D pictures of what's beneath the surface. That's a hugely data-intensive task, and parallel workers are perfect for it because each little chunk of subsurface data can be analyzed independently before being combined into the final image. In medicine, GPUs make it possible to analyze 3D scans, such as MRI or CT images, more quickly and in higher resolution. They also help simulate how molecules interact, which is a key part of designing new drugs. Those simulations involve countless particles and forces, all affecting each other. Being able to simulate many interactions simultaneously is a natural fit for a GPU's army of workers. In finance, GPUs are used to run massive simulations of different market scenarios. For example, if you want to estimate the risk of a complex financial product, you might run the same calculation many thousands or millions of times with slightly different inputs. Each run is similar and independent of the others, an ideal job for parallel processing. In imaging and video processing, GPUs have become the go-to tool for tasks like noise reduction, enhancement, and pattern recognition. Whether it's improving low-light security footage, compressing video, or recognizing faces and objects, these jobs all involve doing the same kind of operation over and over across lots of pixels or frames. And of course, one of the most famous areas today is artificial intelligence. Training deep neural networks involves huge numbers of simple, repeated mathematical operations on large matrices of data. GPUs are incredibly good at this, and CUDA's model for organizing work and data fits naturally with the way neural networks are structured. That's a big reason why the modern AI boom was even possible. What ties all these applications together is the same basic pattern. Lots of similar tasks that can be done at the same time on different pieces of data. CUDA doesn't magically make every program faster. It's not ideal for problems where each step depends heavily on the one before it and can't be broken into parallel chunks. But for the right kind of problem, this architecture and model are game-changing. The story behind all this is, in a way, about making parallel computing feel less scary. For decades, using many processors at once was considered difficult and specialized. You had to think about low-level details, manage communication and synchronization between different machines, and often rewrite your program entirely. CUDA's contribution was to say, here's a way to keep your usual way of expressing an algorithm, but now you can scale it out to thousands of workers with relatively small changes. Under the surface, there's a lot of sophisticated engineering, hardware that can juggle tens of thousands of tasks, memory systems that try to feed all those workers efficiently, schedulers that keep everything running smoothly even when some parts are waiting. But the philosophy is to hide as much of that complexity as possible behind a simple, consistent model centered on grids of work, teams of cooperating workers, and a clear memory hierarchy. So the next time you hear the term graphics card, don't just think about gaming or pretty visuals. Think about a parallel engine, carefully designed neighborhoods of workers, whiteboards of shared data, and a project manager CPU coordinating the show. Think about scientists, doctors, engineers, traders, and researchers all over the world using the same architecture, originally built for drawing triangles and pixels, to push forward their fields in ways that weren't practical before. If this explanation helped you see GPUs and CUDA in a new light, I've got a small favor to ask. Please hit like, subscribe to the channel if you haven't yet, and drop a comment telling me what part of the story clicked for you. Was it the mural analogy, the workers in neighborhoods, or one of the real-world applications? Your engagement really does make a difference. It tells the algorithm to show this video to more people, and it tells me to keep making more deep, accessible breakdowns of the technologies shaping our future. Thanks so much for watching, and I'll see you in the next one.